So last week, we were going over, like all last week was basically Newton's second law, except Monday we had a test. Okay? So the rest of the week has been Newton's second law stuff. And what we're going to be looking at here today is more of the really in-depth sum of all forces kinds of questions. Okay? And this is one of them. We call it a static condition example because the object isn't moving. Now, if the object isn't moving, what's my net force? 0. Yeah. Okay. All the forces are balanced. Okay. That's kind of a Newton's first law situation. But we still look at it as kind of Newton's second law. So what I want to do with this question here is draw the picture. Right? So I've got a sign that's got a mass of 35 kilograms. Okay. And it's hanging from two different buildings. Cable 1 is angled 55 degrees below the horizontal. Okay? That's a 5, not a 3. 55 degrees below the horizontal. And the other one is horizontal. So this is cable 1. And then this is cable 2. Okay, so that's our situation. We're trying to find the tension in cable 2. So where do we start?
Find the force of gravity.
Yeah, find the force of gravity. Gravity is clearly acting on this as it's hanging. Okay, so that would be the first thing we would want to do. All right, so we're going to get 343.45? 35 newtons. 343.35 newtons is our force of gravity. Now, that's the only force I can calculate kind of right off the bat. The rest of it I have to look at and think intuitively, kind of look. Now, can cable 2 hold any of the weight? It can't. Which way does cable 2 pull? Horizontal. Which way does gravity act? Right. So cable 2 is not holding any of that 343.35 newtons. Which cable's holding all of it? Cable 1. Now, that doesn't mean that the tension in cable 1 is 343.35. Because 343.35 is vertical. Cable 1 is angled. So what part of cable 1 is 343.35 newtons? Not the resultant. The resultant is the tension in cable 1. This one right here.
Yeah.
This part. Okay? The vertical part. This is pulling somewhat to the side and somewhat upwards because it's angled. Cable 2 only pulls to the side. That means that this side, the vertical component of cable 1, is what's offsetting the force of gravity. Because it's the only thing in the whole question that can actually pull vertically. All right, so now that I know that number, and that's the only other number I really need, how can I use it to calculate the tension in cable 2?
You can use the angle and the vertical force of the first cable to find its horizontal force. That should be the same as the tension in cable 2.
Right, that just should be, has to be, because the sign's not what? Moving. So we've already done the vertical part. We've made the net vertical force 0. The vertical part of the cable 1 is offsetting the force of gravity, which is downwards. Now, the horizontal component of cable 1 is what's pulling against cable 2. And that's what's keeping the sign from moving, is the fact that those two forces are balanced. So if I find the horizontal component of cable 1, that is equal to the tension in cable 2. Right? So there's not a lot of math to this question. Like I had to calculate the force of gravity, and I'm going to do one trig calculation, and I'm done. Okay? This would be like a 4-mark question on a test. But there's a lot of thinking that goes into it, okay, before we get to the math. So my next calculation is I have the opposite side. I'm looking for the adjacent side. So the trig function I'm going to use is tan. Okay? It's going to be 10 to the minus, sorry, not 10 to the minus 1. It's going to be the tan of 55. Okay, so I'm going to go and I'm looking for the adjacent side. So tan of theta equals opposite over adjacent. Okay, and so I'm going to look for the adjacent side. So that'll be adjacent equals the opposite side, 343.35, divided by the tan of 55. Okay, so the tension in cable 2, which is equal to the force I just calculated, is 2.4 times 10 to the 2 newtons. Okay, now, can I put a vector on that? I can, but I'd be wrong. Okay, the question asks, what's the tension in cable 2? Tension is simply how tight the cable is. Now, if it said, how hard is the cable pulling on the sine, then I would say 2.4 times 10 to the 2 newtons to the right. If it was how hard is the cable pulling on the wall, it would be 2.4 times 10 to the 2 newtons to the left. Okay? In those cases, I could give a vector. In this case, I cannot, because it's asking for how tight is the cable, which kind of is both ways. Everybody all right with that idea? Okay, so do we understand how a static example works? Okay, the key part to a static example is that the net force is 0. Okay, that tells you all the forces add up to 0. That's how we knew that this vertical force was equal to the force of gravity, and how this horizontal force was equal to the tension in cable 2, because we knew the net force, the vector sum of all forces, was 0. That's the key to a static question. So, what if I gave you one that looked like this? I drew that wrong. Hold on. Okay, so let's say that there's $60 between those two cables. I want to find the tension in the cable. Let's say cable A. Did we look at one like this on Friday? I feel like we did. Maybe it was my period 3 class. Okay, see if you can calculate the tension in cable A. So it starts out the same as the last one. Obviously, the main force here pulling downwards is the force of gravity. And it's going to be 196.2 newtons. So there has to be 196.2 newtons pulling straight up. Okay? Here's the mistake people make. They're like, oh, all right, so this force here is 196.2 newtons. But it's really not. That force is split between two cables equally. So each cable only pulls with half that much force. That way you get 196.2 up and 196.2 down. Okay? If we say that each one of these cables has this side be 196.2, then there's twice that much force pulling up, and this thing is flying upwards, okay? Which it's not doing. So I have to keep in mind that, yes, there are two cables pulling on this 20 kilogram mass, so each one only bears half this number. That makes the middle 98.1 newtons for each cable. Now that I have that, okay, and I know that this angle here is 60, that means that for each triangle, the angle is 30. And now I can find the hypotenuse. Okay, so what I've got here is the adjacent side. Sorry, I got that wrong. I was thinking it was the opposite side. I did it wrong. So that's not going to be the answer. Okay, so my adjacent side is 98.1. My hypotenuse, which is what I'm looking for, the tension in the cable, is here. Okay, so if I'm going to find that number, I got to go that cos of 30 equals adjacent divided by hypotenuse. Okay, and then hypotenuse will equal 198.1 divided by the cos of 30 degrees. Okay, so I got that one wrong because I did trig wrong in my head. I shouldn't do trig in my head. I should have heard that. Okay, everyone following what I'm doing here? Okay, so I know this side's 98.1 for cable A. I know this side's 98.1 for cable B. Okay, so I'm finding the hypotenuse of the triangle, okay, and I'm simply going 198.1. Okay, why do I have one? I have just 98.1, not 198.1. Sorry, guys. It's Monday. That's what I'm going to blame it on. 98.1 divided by the cos of 30. Okay, so that side's 113 newtons. So actually 1.1 times 10 to the 2, because we only have two significations here. All right, so there's the trick to that one, is recognizing there's two cables, they're splitting it equally. Again, we only had to do two mathematical operations. Find the force of gravity, mass times 9.81, and then a trig calculation. So lots of times, our stuff just comes down to simple operations. There's not a lot of math in there. Okay, our vector sum of all forces step was really easy here. We just had to recognize that it was 0. And we didn't have to do a mass times acceleration because we knew that would also be 0. Okay, so it ends up, now we're looking for missing forces. Okay, questions on that one? Okay. All right, we talked about systems and pulleys last week. This is just like the lab we're going to do tomorrow. So I want you to copy this one down and see if you can calculate the acceleration of the 5 kilogram mass, knowing that there are 32 newtons worth of friction between the 4 kilogram mass and the surface that it's sitting on. Okay, give you some time on that one. All right, so if we're drawing a free body diagram of this situation, obviously we've got a force of gravity here, okay, that's pulling on the 5 kilogram mass. So that's going to be m times g, so that'll be 49.05 newtons. Okay, we also have a force of gravity here and a normal force right here. Do I need to worry about those two forces? I do not. They cancel. Okay? That box is not moving vertically, therefore the net force vertically on that box is 0, so I don't need to concern myself with those two forces. The force I do need to concern myself with is this force of friction here, that is 32 newtons. All right, so I'm trying to find the acceleration of the 5 kilogram mass. What do I do next? Sorry, I saw your hand creeping.
You could take, would the force of gravity not affect the forward motion of the 4 kilogram one as well? So,
It does,
right?
yes.
But then you have to account for that and then the friction for the actual forward force.
Right. I've got to find the net force here, right? The forward force acting on the system. That's the key part of this. Acting on the system, not the 5 kilogram mass. That's the common mistake that's made if I word the question this way. Everybody gets focused on the 5 kilogram mass and they forget that the whole system, all 9 kilograms, has to move, has to be accelerated, is being acted on by the net force, whatever that happens to be. Okay? So what I want to do is simplify this diagram down to this. 9 kilograms worth of mass being pulled in one direction by 49.05 newtons worth of force and being resisted by 32 newtons worth of force. Okay? That's what's going on here. Okay? Is that all 9 kilograms are being accelerated by whatever the net force ends up being. Well, the net force ends up being 49.05 plus negative 32, which should give us 17.05 newtons, okay, worth of force. Can I calculate the acceleration now? What do I divide by, 5 or 9? 9, right. Okay, so the acceleration is F net. divided by the mass of the system, so 17.05 divided by 9, so we're getting what, like 1.8? 1.89, but we only have one significant digit, so it's 2. Okay, meters per second squared. Can I put a vector on this one? Yes, because it asked about the 5 kilogram mass.
Would we not have, oh, never mind.
Sorry, the masses only have one
Yep.
significant digit, yeah. Okay? Okay, so that one I would put a vector on because it did ask about a specific part of the system. Okay. All right, questions on that? All right, now I'm going to throw one at you that's a real curveball. We already did that one. We did that one. And we did that one. And we did that one. Did we do that one? Yeah, there's the constant velocity one. And we did the child on the slide. Okay, so I'm going to make this one up. This is really going to make you think. Sorry, doing some math in my head. Okay, I think that'll work. It should work. All right, I want you to calculate the acceleration. Oh, sorry, this is supposed to be 40 kilograms, not 4. That definitely won't work at 4 kilograms. Well, not the way I want it to anyway. 40 kilograms. Okay, yeah, so I want you to calculate the acceleration of the 51 kilogram box. Okay, let's just quickly look at the free body diagram. I'm not going to spoil it for you unless you're already done. Okay, so force is acting in this system. Okay, got force of gravity here, okay, which is 40 times 9.81. All right, so we got 392.4 newtons. Okay, we got a force of friction that's 65 newtons. How did I know to draw it that way?
Because it's going to be working against the force of gravity, which is pulling the 51 kilogram box off the ramp.
Right. I'm assuming, and I could be wrong, but I'm assuming that the box is going to move up the ramp because of this setup. It should. Okay? I know a lot of people look at that and go, well, but this mass is bigger, so it should go this way. But remember, it's on a ramp. Gravity is pulling directly on the 40 kilogram mass. Gravity is indirectly working on the mass on the ramp. That's that whole F parallel thing, which, by the way, we got to calculate. Okay, so you got your force of gravity here, okay, which will be 51 times 9.81. Okay, so 500.31. And so this is our other force, F parallel right here. Okay, remember that it's this side of the triangle. That angle is the same. Okay, so we're going to be looking at 250.15 and 15 something. I'll just calculate it. $250.155. Okay, so 250.155. Okay, so I got 392 going that way, and I've got the sum of these two going the other way. Okay, trying to find the acceleration of that box. Give you a couple more minutes. Okay, so can we calculate the net force? Right, so we're going to take our sum of all forces. Okay, so that'll be our 392.4 plus negative 65 plus negative 250.155. Okay, is it okay that I just add them even though there's a ramp and an angle? It is. I already took the angle into account. That's why I have that parallel. Okay, so really now what's happening is this. 91 kilograms, okay, is being pulled this way by 392.4 newtons, and this way by 315.155 newtons. Okay, that's really what's going on here now, right? I've got 91 kilograms worth of mass in this system, and those are the forces that are acting on it. As soon as I get all the forces identified, this whole complex, really like anxiety-producing situation of an inclined plane and a pulley disappears, and it comes down to this. Okay? These two forces acting against each other on 91 kilograms worth of mass. Okay? All right, so when I do that, okay, I'll get my, so 392.4 minus 315.155. I put plus, it's supposed to be minus. All right, so my net force is 77.245 newtons. Okay, I want the acceleration of the 51 kilogram mass. What's my next step? Divide the net force by the mass of the system, not of that one mass. The whole system has to accelerate. Okay, so we're going to have our 77.245 divided by 91 kilograms. Okay, so our acceleration is 0.85, because that's all we have, 0.85 meters per second squared. Why can I write a vector? It asked about a specific part of the system. It said specifically the 51 kilogram mass. Therefore, I can say it's accelerating up the ramp. Okay, but it said the system, then I'd only be able to say 0.85 meters per second squared. All right? A question like that has been on the final exam every year. How did I get the 200 in? Here? So I calculated F parallel, okay? Since it's the opposite side of the triangle, I went sine of 30, which is 0.5, times 500, 0.31. So 0.5 times 500 comes up to 1/2, yeah? Okay, any other questions on that one? All right. So this is kind of where we're at. We understand Newton's second law. We get this whole vector sum of all forces, m times a thing. Now I need to throw as many weird situations in which it applies at you and see if you can adapt. That's the real challenge with Newton's second law. So what I would like to be working on right now, I'll pull it up here, but there's a bunch of Newton's second law worksheets in your digital workbook, and they have a variety of different types of Newton's second law problems. Okay, so if we're looking at, let's say you guys could start with 19 on page 2, the end of page 2, question 19. And keep moving on from there, okay? You can do any of the ones from 19 on. There's a page after this one that's just inclined planes, and a page after that that's all vectors. Okay?
right? So there's a whole bunch of different types of problems here that you guys can try, but for right now, let's say from 19 on.